Right, folks. So like I mentioned, coding agents have been tremendously successful. Now we're all wondering, what's the next big thing? What is the next step? And you've presented your personal directions for this. So one feature that I think is pretty common among all of the new directions that people are pursuing is it's getting harder and harder to generate those rewards that we can use to power reinforcement learning. Right? So I'm curious, how do you think about the difficulty of getting rewards in your particular domain? Do you think there are ways of new techniques you can use to get those rewards, or how do you think of this? So starting with Ed, maybe.
Yeah, the difficulty with rewards is really because the predominant paradigm over the last couple of years have been about using correctness as a feedback to the RL process, and the reward functions were pretty easy to build when you have a correctness that's built into the question that you're asking. But there are many questions that we want to ask, including in science, as Richard was mentioning, that the answer may not be correct or not correct, may be more somewhere in between, and the challenge in building those reward functions, it's not just in figuring out, sort of some approximate solution to that, but it's rather that the RL process is very, very good at finding loopholes in the reward function when it's not a black and white kind of answer. So we call this reward hacking in the actual development of the algorithms. And we see it manifests in actually model instabilities when we have these more complicated reward functions. To summarize, therefore, I think one way to think about this whole RL thing and using correctness function is, as I mentioned in my talk, it's a little bit like teaching your kids. When it's wrong, you just slap them in their butt, and then you don't give them any more explanation why they were wrong, right? Other than just figure it out. And so I think this kind of bottom-up training process is actually a very, sorry for saying it this way, but it's a very dumb way of teaching.
Right.
I think actually what we're seeing with distillation and SFT coming back into vogue, what we're seeing is actually a lot more top-down processing in teaching. Where some people find it distasteful because it feels like we're using human brains to teach machine brains, if you will, and it doesn't feel as emergent. But that's what I believe, is that we need to have more top-down processing injected into the AI training process.
Thank you. Yeah, Dosh, how are things looking with the furnace? Is it generating rewards?
Yeah, so there are two kinds of issues with furnaces, right? So one of them is, as Ed mentioned, you don't always know if the thing worked or not. Like, you take the thing out of the furnace, it's not actually obvious, it might have partially worked. And in fields where LLMs and RL has made a huge impact, I think there are two specific things that really help. One is there is a very clear yes or no. We just talked about this. The other one is how much of the variables are in the context. So when you're programming, when you're doing theoretical computer science, math, all the context you might need could be available to the LLM. The problem with physics is, right, we have more atoms than we can track. And this is why thermodynamics was a big deal, because in the 19th century, we realized instead of having to model 10 to the 23 atoms that make up a mole of matter, you can just use a few variables like pressure, energy, volume, etc. So we have to give up on providing all the relevant context to the LLM, because there's no way we can do that. So then the question is, what can we provide, and is it sufficient? That's why it's really important to add as much metrology, characterization as possible, maybe even more than before, and just provide as much context as possible about what happened in the furnace or in the thin film chamber to the LLM.
Yeah, I think those are all really interesting. I mentioned it in the Eureka machine, right? You have human current knowledge, you have scientific measurements, then you have simulations, which are hard at scale with current computers, and then you have to have real-life experiments, and then hopefully you can get some of those inner loops resolved. I think in terms of reward functions, There's also this whole idea that I've been thinking about recently on metacognition. I think if you truly have something that's super intelligent, it wouldn't just robotically do exactly what you ask it to, right? There's, in some sense, no research right now on subjective functions rather than objective functions that we're all working on, right? And so one way that these can emerge is if you give AI the right environment. That is not as easily reward hackable, which I think is the #1 concern for safety. Also, it's just alignment. But I do have to say that I'm sort of cautiously optimistic, and I want to maybe invite folks to see Whisper Flow, which is like a voice recognition app of sorts, as a first sign of things to come as AI gets better. Whisper Flow doesn't exactly write what you say, it writes what you mean. And most AI currently does very poorly, like exactly do what you say, like make this benchmark number go higher. But you didn't mean like by hacking Hugging Face, you know, like, and so, but I think eventually that will get resolved.
Cool. So one thing I'm really curious about, because these agents, they have this promise of accelerating us. Are you actually seeing real-world acceleration from using your models? So Richard, how are things looking at Recursive?
It is kind of nuts. Like I really think like we have a fairly small team, but they act as if they're like an order of magnitude more people. Oh. It's much less about headcount these days than it is about agent count. And if you want to, yield and wield sort of like the hundreds or even several thousands of agents, you need a lot of compute. And so I think the future in which a lot of these forward-leaning organizations actually use more compute or spend more on compute than on headcount and people is very likely to happen, especially at the frontier. And yeah, I would love to hear from you actually also on like how much robotic process automation can you do now, and is the bottleneck the intelligence or actually just the mechanics?
I mean, for the experimental side, I feel like the biggest bottleneck is characterization and analysis, because it's not too hard to just mix things and then try 1,000 things at the same time. But what's really hard is to understand what you actually made. And this is actually really good news, because AI can do really well at this. Like you can show AI how to do, for example, XRD refinement, how to use read-well refinement tools, use simulations in the loop, and it's like doing characterization analysis well isn't as hard as discovering something new. It's just like using the tools correctly. And I think this is great news for science, because now we can try many more things and intelligently analyze them than before. Of course, we do a lot of coding, like the theoretical physicists do coding, the experimentalists do coding, and LLMs have completely revolutionized that, of course. Also on the simulation side, so force fields are these things that people have used for more than a century to approximate quantum mechanics. I think one could argue that even Einstein's first paper was a force field paper. And in the last 10 years, because of graph neural networks, force fields changed permanently. And it's amazing now how much of the periodic table we can model without even doing quantum chemistry. So yeah, really exciting on the capabilities side.
Are people at Google using agents to accelerate themselves?
Yeah, we're obviously using agents in our coding work. But I think as Richard and Dosh were just describing, I was realizing that maybe I think about the problem a little bit from a weird way, if you will. The reality is that I think about that is that it has been a decent amount of tension that's happened ever since the beginning of sort of the chain of thought era, is that agent harnesses is really the evolution of prompt engineering to today, right? Like, because people started with prompts, and then they figured out that they can put more things in the prompt to get the model to do what they wanted it to do. And then they realized they should programmably put these prompts together. And then they figured out things like LangChain to figure out how to chain prompts together so to get it to do more complex tasks. And then they realized they can just put a whole program around the generation of the prompt and how many prompts and how to chain them together. And then that evolved into agent harnesses and coding harnesses. So that whole evolution, of course, all of us have been in the field and have been watching that going. But the tension that is inherent in your question is there have been, for 3-4 years, this debate about how much should be in the model and how much should it be in the programmable framework, the agent harness that we call it now. We used to just call it programmable LLM frameworks. And in fact, I'm sure in the audience today, there are people who are trying out different agent harnesses with different models, and they're realizing that they're kind of evaluating all pairs of these relationships. Like they're using a strong, very structured agent harness, working with a very weak model, and then when they have a very strong model, they try to put less harness around it. By the way, it's just very interesting to me that we use the word harness. The word harness obviously comes from horses. The reason why we're called engines horsepower is because the Industrial Revolution, with engines, we all became engineers, right? Like we're supposed to work on engines, right? Like tightening screws and stuff like that. And then, the engine mount is basically the harness, right? So the reality is the prompt engineering and the harness is kind of like the structure that's trying to get the engine to do what we want it to do, right? So this tension between the harness and the model capability. And people are realizing when you have a strong model, you should use a weaker prompting technique and weaker programmable harnesses. But when you have a weaker model, you could mitigate its capabilities using a stronger harness, a more structure. But however, I think people are also coming to the realization when they do this, that the two together can only reach a particular performance level. And there is a plateau that we can't seem to go over at the current moment. And that is actually the major bottleneck or barrier currently facing the industry, in my opinion.
Yeah, that's the frontier.
That's literally the frontier right now.
Actually, yeah, maybe jamming on that, I do think the whole field of AI is kind of stuck below what I call anthropic bounds, not just the company, but like this idea that like we measure models in terms of ELO scores of which human said this model is better than that model. We measure a lot of our benchmarks based on how many of the human-designed labels and human-designed classes and tasks did you get right in this subset of images and like reasoning questions and so on. All of those have implicit and sometimes very explicit human bounds. Like if you're 100, you can get 100 out of 100% of the questions right, then that's the maximum you can get to. And yeah, maybe humans get like 95 and you get like 5% above the human baseline, but that's it. Where do you go from there? And the only way to get out of that is through simulations and some verifiers where you can then get superhuman capabilities or in these open-ended evolutionary environments.
Well, now I have a really, really tough question. So let's see if one of you can find an answer here. But
get ready for this one.
So we're all at the frontier, and at the frontier you need access to tremendous compute resources. You've got colleagues that are experts in their field, but there are so many people in academia and especially PhD students out there who don't get access to those resources today, but they still want to contribute to the frontier. They want to contribute to agents and the future of agents. Do you have any tips for those folks? Like, what are the directions? What are the ideas that they should focus on where there's a potential to have big impact with fewer resources and contribute to these frontier efforts? Like anyone that has something that comes to mind?
I think there's a ton of opportunity still. There's so many underexplored areas and application areas of AI too. Sure, like maybe the research area of pre-training and mid and post and RL training is not the best one for PhD students at a university, but I had this paper in 2018 on a 2-level reinforcement learning setup called the AI Economist, where you essentially had agents that just optimized their own utility functions, and you can make assumptions based on how many hours would people want to work. And some people are willing to work 100-hour work weeks, and some people only want to work 10-hour work weeks, right? And then they're kind of unmotivated. And so, long story short, you can then have this simulation of agents that are economic agents trying to optimize their own utility, collect resources, block others, build monopolies, whatever. And then you had an AI economist that would set taxes and subsidies. And basically could now simulate billions and billions of years of taxation and subsidization, essentially political philosophy, and try to find the sort of best way to set these taxation schemes and tax brackets and so on based on a goal that you gave it, like productivity multiplied with equality or sustainability or whatever you politically care about, middle class, like whatever politicians say, right? Now, what's interesting is that paper never had its sort of GPT moment where someone actually took that idea and massively scaled it up. And so the whole field of economics is still like pre-AI era. Like when you look at economists, there's one really famous economist from Berkeley, actually, Sayez, right? He invented this famous Sayez formula, and it's provably correct in a one-step economy, where there's no adaptation, there's no adjustment, or no temporal sequences, and so on. That's the state of the field of economics. And if you now realize like that AI could do so much more there, and you can simulate people better and better, especially in their aggregate statistics, you can realize like there's so much low-hanging fruit for PhD students to take AI and apply it to economics. And that is just one of many examples. There are still so many other fields that you can research in and then combine AI with that are extremely underexplored. And I'm excited that like venture capital is now excited also about chemistry and some more physics and obviously biology, but there also is still so much low-hanging fruit to apply AI to these various scientific fields.
Any more ideas for the
Yeah, I mean, I would say, so it's hard to predict the future, right? Like, in 4 years, if these robots are as dexterous and intelligent, creative, has a sense of style, as humans, I think this answer gets very complicated. But today, I think it's very easy to say robots are not as dexterous, they're not as creative, they don't really have a sense of interestingness. And in that case, I think what the students should study, in my opinion, is the fundamentals. So, for example, today, very practically, if somebody as a scientist applies to periodic labs, to me, it doesn't make too much of a difference if they've been using agentic tools to run simulations, because there's something you can probably learn how to do pretty quickly. The thing that's very unique and unfortunately getting more and more rare is just people who understand the fundamentals about like the physics you're studying or the experiments you're studying. I mean, I used to joke, but when I was at Google, we used to have these interns coming in, and I used to hire interns from physics labs to do physics research. And they'd be so much stronger on the machine learning than the physics. And maybe I'm just being like too uncreative here, because back then I used to worry that, as you know, all the simulation tools are in Fortran and C and C++, and all the kids are only doing Python. I was like, oh, are we screwed? Like, what's going to happen in the future? But I think that's resolved now, right? Like now, even though we don't have it yet, we can see that these agents will be able to give us Python code or JAX code given a Fortran package, great. But there are still a lot of things that these machines cannot do, like being creative about the fundamentals, coming up with like a true innovation on our understanding of the universe, being able to run experiments, coming up with new experiments. So at least like from my selfish perspective, I really feel like the big alpha today is understand the fundamentals of the application, and then you can connect it with machine learning.
When I was working at Google Brain, when Doshi and I were both in Google Brain, when we were before the chain of thought era, I remember Danny Zhao came to me, and he said, all those people in Google Brain with control over the resources makes it very difficult for me to do research. So the same complaint in a way that you're kind of inherent in the question that you're asking. And he said to me, how do I deal with this problem? I said, I don't know, go think about how humans think, and maybe we can figure out a way to like inject these processes into the model. And then one day he came to me, and what I'm about to tell you, I hope doesn't get me fired from Google, by the way. One day he came to me and he said, I want to do a bunch of experiment on GPT, is that allowed? And it's like, because we're at Google, we should be using Palm. That was our model, right? And so we should be using Palm. And it's like, I can't get my hands on chips to do all these experiments on Palm. I don't have access to the checkpoints, blah, 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 blah. And I said, can I just use GPT? Who will pay for it? And I pulled out my credit card and I said, here's my credit card. So he charged all these like API usage on, this is before ChatGPT, okay? So this is no free resources. You actually have to buy API key and all that. He racked up couple $1,000s worth of charges or something like that. And then we wrote the paper. That became chain of thought. So even then, Google was spending billions of dollars already to train these large language models. And here comes a new idea that was top down rather than bottom up. Not thinking about next token prediction, but rather thinking about next idea prediction. And I think we ultimately spent less than $10,000 to come up with the next idea. Now, you might say, oh, wow, that was 3-4 years ago. I think the paper was January-ish of 2022, 21. And so you say, oh, well, then that's not possible in 2026. Well, where were you when Peter Steinberger was working on OpenClaw, right? Like, I would argue a lot of people really started to pay attention to Agentic programming framework when he really put all these technologies together, and that didn't cost like billions of dollars, right? He was just some dude. I think he presented yesterday. I was flying in from Taiwan last night, and so I didn't get to attend his talk. But I mean, here's a guy who's just like, oh, I'm going to experiment with Agentic frameworks, and then he come up with some new thing about how to think about the problem. So I think the state that we're in, that when academia are complaining about this, it's a little bit like there are many mature fields that have moved like this. Like experimental physics, at some point, people are going to complain, I don't have access to a linear accelerator. Or when I was working on supercomputing back in the 90s, oh, I didn't have access to a Cray YMP. So therefore, I don't have 2.6 gigaflops or whatever it is to do. By the way, does anyone know why we were investing in supercomputer in 1990? Does anyone know? Anyone can raise their? Yeah, what's the reason? What kind of simulations?
Nuclear.
That's right, nuclear simulations. It was because of the nuclear ban treaty. We wanted to simulate real physical processes, so we built supercomputers. That was the reason. And then people started, came from a complaint about the fact that we can't blow things up anymore. So we're going to have to come up with a new way understanding physics, right? And that was supercomputers. So we're very good at coming up with new ways of looking at old problems as well as new problems. And so I think computer science as a field or AI as a field needs to continue to look at this. When everybody is working on RL, you should be thinking, what's the next idea?
Yeah, it's kind of interesting. Like you touched on an interesting point, which is like I still remember in 2010 when I submitted my first neural nets for NLP papers, they got desk rejected. People are like, we don't do neural nets in NLP conferences. They didn't even look at the experiments. And even when we submitted a paper for prompt engineering where you had one neural network to answer any and all kinds of questions, the reviewers literally said that it makes no sense. You should never have one model to try to answer different kinds of questions. They should all be different models. And it was unfathomable for them, and they rejected that paper too. It's all public on Open Review and that ICLR submission on Deca NLP. The paper eventually got cited 5 times by the first GPT paper, and it kind of had its run now. But there's now almost like a monoculture that is similar to the monoculture from 2010 when it's all anti-neural nets, and now it's almost all only neural nets. So I think it'll be good to start thinking again about completely different approaches. Not everything is a transformer. Transformer is just one sample in a very large equivalence class, and I think there are other better classes of algorithms still to be explored. I think compute substrates, obviously we can do better. We know the brain has more flops per watt than any of the hardware we have. So there's so much research there still to be done and so on. I feel like there's no excuse for researchers in AI and outside of AI not to still do academic work.
Yeah, there's a good lesson in resilience there for PhD students as well. Just because your paper gets rejected, it could still be the next big breakthrough. Nobody really knows the future. So it's a lot of folks in the field tell me similar stories about their big breakthroughs. One thing I would add is while the research at the frontier is getting more and more expensive and challenging, at the same time, we're also seeing some of the tools being more and more democratized. So I'm thinking especially of open weight models, for example. So if you wanted to start off with a really capable LLM or really capable agent, you can actually take a powerful open weight model today and then do a lot of interesting research and development on top of that. And even the tools for post-training and reinforcement learning are getting democratized. I mentioned the River AI API earlier, and Tinker is another example of these kinds of tools where even with a very limited budget, you can do really, really interesting work. So I think it's also a big opportunity for researchers to be able to do really actually frontier work without a huge cost attached to it. So we're getting to the end of the session, so I wanted to go to the big closing statement. And so I wanted to ask you folks, let's make a prediction for the next 12 months. We've seen this year was the year of coding agents and the incredible economic success that came with them. Over the next 12 months, what will be the next big agent breakthrough? Where do you see the big impact in the world and economic impact as well? So maybe starting with Ed.
Well, as many of you know, if you especially attended last year's summit, I was making a prediction that personalization was going to be really big. And I know Richard has also worked on personalization as well. It's been very surprising how slow it has been, to be perfectly honest. But I think a lot of the issue has been around data and the sparsity of data for personalization. In the consumer space, my prediction in the next 12 months or so would be that usually it takes like 3 tries for these things to succeed. And I think there will be a good try probably within the next 12 months or so in this space. And most of the issues will be centered around 2 things. One is data that I mentioned, the integration. The other is actually having to do with being able to really make good inductive inferences and reasoning, because so much of the model these days are very focused around deductive reasoning. You bought this, therefore I think you were going to buy this next. Like you bought a bicycle, so you're going to need tires or something like that, right? Like there's a reasoning chain that's very deductive like that. But actually a lot of the recommendation tasks, the personalization tasks, are very ambiguous and they need more induction, right? Like, if you bought a turntable, we can infer that maybe you like classical music, for example, or jazz. I'm a big vinyl collector. So by the way, one of the reasons I came up to Berkeley is because Rasputin is not far away from here, so I could walk over and peruse the aisles there. But that's an example of induction, right? Like Google Maps should be recommending, hey, by the way, Rasputin is less than 5-minute walk from here. You should go check it out. Right, so that's the kind of inductive reasoning I think in the future in the personalization space we're going to see within the next 12 months.
Yeah, Josh?
Yeah, so speaking of induction, I think if you look at what happened so far in terms of how LLMs and agents did something incredibly different in the sciences and math, I think it's easy to say that it's been in math, theoretical computer science, and programming. So if you were to do induction, the next step should be fields where pure theory goes a long way. So maybe this will be your expertise with the particle theory, or maybe it'll be in astrophysics, I'm not sure. It could also be computational physics, where there's some really difficult problems in computational physics. That's not necessarily like the real universe, but still very important on its own right. So it could be that as well. I don't know if it's going to be in 12 months. Again, like it's really hard to predict the future, but it does suggest that, like, given the current trend, that could be the next step.
It feels like there's a lot of results in mathematics coming out every day now. So getting more and more theorems proven. So I think that's a very promising bet. Yeah. Richard?
Man, it's going to be an exciting 12 months. Maybe I'll cheat by doing 3. I think number 1, we'll see more proactive consumer interfaces to these models that capture more and more of your context, and hence will make sort of recommendations before you ask for them. There are already a few startups that are growing a little bit here and there, but I think more of that is to come. I think in biology, we're going to see the first and much faster clinical trials and getting more and more drugs and proteins developed with AI that are then succeeding at a higher rate than currently as they get into later stage trials. And then we're going to have the first baby forms of recursive self-improvement. And I'm cheating there because the best predictions are those that you're going to work on yourself and try to make them true. So I think it's feasible. It's happening. We're very confident, and like it's then of course a question of, well, but how much compute do you give it, and how hard are the tasks that you give it to work on, and the environments, and all of that. So sometimes people think that there's going to be this hard takeoff scenario, and despite being extremely excited and optimistic about AI, the hard takeoff scenario where everyone loses their jobs or the AI kills everyone, all of these are highly unrealistic sci-fi. And so I also predict in the negative that none of the doomsday scenarios will happen at all whatsoever. And just like GPT was too dangerous to release to the world, there will be no open source model that will be too dangerous to release to the world.
Thank you so much. And I hope you all enjoyed this little glimpse at the frontier. So let's thank the speakers.
Thank you.